Okay, so in this third and final video on driven oscillations, we're going to talk about an inductor in series with an AC battery. Right, so I'll draw that like that, right? And that's just simply in series with an inductor, which can be drawn like that, right? This battery is generating a current, which I'll go or draw that way around. And so this creates a fairly simple Kirchhoff's loop rule equation, which is EMF minus the voltage through the inductor, and that equals 0, right? Remember that this voltage is equal to minus L di dt, right? That's the voltage across an inductor. So we can see that the EMF, which is sinusoidal, right, sine omega t, that's equal to VL, which I'll keep in this form for now. Okay, because it's hooked up to an AC battery, the voltage through the inductor also has to be varying sinusoidally. Okay, so that's why I wrote it like that. And again, that's the voltage across the inductor. And that's what we want to compare to the current across the inductor. Okay, and so like before, we can write down the general formula for the current. I of t. And so we want to get our current through the inductor in this form. Right? We want to get it in this form here, right? Some initial current times sine of stuff, right? In order to be able to accurately compare to the voltage, because that's sine of stuff. All right, so the voltage for an inductor is, well, let's do L di dt, right? The minus sign is not here because the minus sign was in the Kirchhoff's loop rule equation right there. So just by itself, it's positive. So L di dt, and that has to equal that. Okay. Now, we want to get an expression for the current. Okay. Well, this is a separable differential equation, somewhat easy to solve. So we have, let's see, I'm going to bring L to the other side and T to the other side such that we have di is V of L over L times sine omega t dt. Now we can integrate both sides. VL over L is constant. And the left side is fairly straightforward, right? That's just, I'll call it I sub L, the current across the inductor. And the right side, we actually need to do a quick U sub. So let's make U omega t. That means du is the differential of that, which is just omega sub d. Chain rule gives us dt. And so plugging that in, solving for dt means it's du over omega. So actually we have an omega on the bottom that we can pull out, times integral of sine u du. Right? Integral of that, well, that's still out front. Integral of sine is negative cosine of u, which is just omega t. Okay? And like before with the capacitor, this out front has to be of the form of a current. Right? It has to be in a current form, which is V over R. So it has to be in the form of V over R, which means that our omega times L is a resistance of sorts. And like before, it's not R, but it becomes a reactance. Let me just, I don't like that. Let me just write it has chi. So now it's chi sub L, which is equal to omega d times L. So now this is the inductive reactance, right? Chi sub L, and that's the driving frequency times the inductance. And again, this has the same units as resistance, and that's ohms, because regardless of if this is a DC or AC circuit, it has to obey Ohm's law. And so this is a current, means that it's a voltage divided by some unit that has the SI units of ohms. Well, because this is an AC circuit, we call that a reactance, chi. So this omega d times L is a reactance, okay? All right. So now, this is the current through the inductor. Notice the form, it's of cosine of stuff, okay? That's not the same as sine of stuff. We have to get this cosine to be sine. But actually, there's a negative in front. So we have to get a negative cosine stuff to be positive sine stuff, right? Luckily, whoops, oh yeah, I need to add a page. There we go. You may remember, you probably don't, but using the fact that we have a negative cosine theta, that's the same as sine of theta plus pi over 2, right? Using that, right? Let me just check, make sure that's the right one to use, using sine. Aha, it's a negative pi over 2. Sorry about that. Using this trig identity, we can put the following equation for current right here into another form. So negative, so that becomes V over chi times sine of omega d t minus pi over 2. And hey, look, the phase constant is kind of generated for us, right? Now we can accurately compare this with, I'll rewrite it here, with the voltage. Again, that's supposed to be, I guess, lowercase. So we're comparing both of these. That means that the phase constant, or the current, is out of phase by a positive pi over 2. Right? Remember the general formula for the current. The general formula here has a negative. Well, if this does too, that means phi has to be positive. And so, for an inductive load, this means that the current is actually lagging behind the voltage, right? Or lagging behind the EMF. And if we were to draw it on the diagrams, right, those graphs, in blue, let's draw, well, actually, let's put half phase and complete phase. Now for blue, if we have a voltage like before, right, let's say it starts there, the current, whoops, that's supposed to be voltage, current in red has to be behind by 1/4 of a phase, which means its maximum has to be, well, right here. Which means that it looks something like that. So now this is I sub L, right? And it's only to the right because the waves are effectively moving to the left. And I'll try and replicate that here. So the voltage in blue, the maximum now is over there. Something like that. And let's do it again. So now we have this. And, well, that amplitude changed for some reason. Not to scale. And lastly, minimum here, go up, maximum, down, minimum. Okay. So from left to right, hopefully 1, 2, 3, 4, the blue waves should be seeming to move to the left. And I'm going to try to do that in the red for current. So now we have this is 0 here, and maximum is right there. 0, minimum, 0. Maximum, minimum, maximum. And right here, let's try to do it. Minimum, maximum. Okay. Did I do it right? I think I did. So in this case, the current, right, at every point actually, not just the maxima, but that's the easiest to see, the current lags behind, in other words, to the right of the voltage. By how much? By 1/4 of a phase. And we see that because this is period over 2, and this is one complete period. So that means this is period over 4, and this is 3t over 2. No, 3p over 4. There we go. Okay, and if we were to draw a phasor diagram in blue, let's say like before, the voltage is at maximum, so VL. That means the current is behind, so thus it's at 0. And again, they're moving counterclockwise at a frequency of omega d, the driving frequency. Okay, so the angle in between them is they are shifted back that way. Actually, let's just do, the angle in between is phi is positive pi over 2. Again, I know you're used to plus angles being counterclockwise, but since they're moving themselves counterclockwise, it's the reverse, right? I should mention that if, hypothetically, if they were moving clockwise, right, if the phasors were rotating clockwise, then the plus and minus would be flipped, okay? So if they were moving clockwise, a negative angle would be what you're used to, and a positive angle would be what you're used to. But in this case, in the book, in this chapter, they're not. I'm not sure why. And so again, the second case, just to show you the rotation, if the voltage through the inductor is at 0 now, right, then the current is up here. All right, so that was showing you that, I didn't write it down, that the current lags the voltage, right, in an inductive load. And we can write that with the acronym ELI, right? The current is behind the EMF for an inductive load. And so putting that together to differentiate between a capacitive and inductive load, you can say ELI, the Iceman. That's a good memory aid, that whole thing there. ELI, the Iceman, right? That will help you remember for an inductive and a capacitive load whether the current leads or lags behind. All right, thanks for watching.